Hello. In this video we're going to talk about the law of large numbers. Now in the last video I slipped in a little sentence which I didn't explain. I said because the probability of drawing a black card from a deck of 52 cards was a half, I said that if we did this lots of times we would expect half those events to be black cards. I didn't really explain that. And that is due to the law of large numbers. So the law of large numbers states, as the number of trials of a random experiment increases, the proportion of times the event E occurs approaches the probability of E. So the more trials we do, the proportion of times that we get what we're concerned with will approach the probability of that thing. We're going to do some experiments. Let E be the event of obtaining a perfect square number on a fair six-sided die. What is the probability of that occurring? So the probability of the event E is the size of the event D divided by the size of the sample space. Rolling a fair six-sided die, the sample space is the set of outcomes 1, 2, 3, 4, 5, 6. And out of those, which are the perfect square numbers? So the event E is the set 1 and 4. They're the only perfect square numbers we can get from a six-sided die. The size of the event divided by the size of the sample space is 2 over 6, which simplifies to 1 over 3. So the probability of obtaining a perfect square number on a fair six-sided die is a third. The more we roll a die, if we count up how many perfect square numbers we had divided by the number of trials we do, the more trials we do, the closer that will get to a third. And we're going to do that trial now. So I am going to run 45 trials of rolling a die. I'm going to record the number that I obtained from that die, and I'm going to record whether it was a perfect square number or not. Let's go. Okay, that's all our experiments. Now I'm just going to record whether they were perfect square numbers or not. And what is the proportion of perfect square numbers that we obtained? We obtained 23 out of 45 perfect square numbers. What would we have expected? We would have expected a third of them, so we would have expected 15 out of 45. So that is a little bit off, but it's not too bad. But I hope this demonstrates what we mean by running a lot of trials and getting the correct proportion. So you see there, we didn't quite get a third. We had 23 over 45, and we expected 15 over 45. But as we would have run more and more and more experiments, we would have got closer and closer and closer to a third. But running a lot of experiments takes a lot of time, but there is an easier way of doing that. And this is a technique that I'm probably gonna use now and again throughout this course, because it's a quite nice simple way of being able to run a lot of experiments. So I'm going to now open up Excel. Okay, I've opened up Excel, and the first thing we're going to do is recreate that experiment we just did by rolling the die. So how do we roll one dice in Excel? Well, we can use the randBetween function, which will sample a random number in a certain range uniformly. And we said that every number on a die is equally likely to occur, and they're between 1 and 6. So this is the perfect model. Yep, that's come out as 1, but every time I refresh the page, for example, if I just type something, it'll change number, type something again, and so on. So we could run this lots of times, and we're going to run this 45 times, but I can just show you we get lots of different numbers out. We are going to want to count how many of those outcomes were 1s or 4s. In Excel we can do that with the COUNTIF function, so equals COUNTIF. If this cell is a 1, it'll come out as a 1, otherwise it'll come out as a 0. If we want a 1 or a 4, we can just add them together. So COUNTIF this cell is a 4, so if it's a 1 plus if it's a 4. Okay, and you can see how this works. If it's a 4, we get a 1. If it's anything else, but every time we refresh the page, if it's a 1, we get it. Now we're going to do this 45 times, so we're going to drag these down to 40. We've used row 1 for a column, so drag this down to row 46. We've done that 45 times. And we've got these 0s and 1s, that was my ticks and crosses, whether these were perfect square numbers or not. And now to find an estimate of the probability, we can sum up this column, because that's how many perfect square numbers are there. And then we want how many trials did we have, and we know we've got 45, but we might want to extend that in a bit. So we're going to use the count, which counts how many numbers there are in a column. How many numbers are there in this column? And we get a probability estimate now of 0.288. So that's slightly less than a third. Right? When we did it ourselves, we had slightly more than a third. Now we're getting slightly less than a third. This is going to become more and more accurate as we get more and more trials. So let's do more trials. Let's say we can do, instead of 45 of them, let's say we do 100 of them. So down to 101. Now what is our probability estimate? Now it's got to 0.29, which is very, very close, which is lovely. So I'd now like to demonstrate how that probability estimate changes as we do more and more trials. So let's make another column, probability estimate. And now we're going to do for each trial, what is the current probability estimate before we have more trials. So this would be the same formula as this, but instead of doing it the whole row, we're going to do it to just where we've got to. So okay, and whether if you know Excel or not, we can fix a few of these values from when we're dragging it by using dollar signs. Okay, so now when we drag this down, what we're getting is a run-in probability estimate. If we've only done 4 trials, our estimate is 3/4. If we've done 8 trials, our estimate is 0.425, and so on. So let's see how this changes as we go all the way down to 100 trials. Okay, we are getting, you can see we're getting around 0.39, 0.4. Okay. Now it's going to be interesting to see how this changes. So we can simply draw a graph of that. And this is a graph that really shows the law of large numbers in action. When you don't have many trials, you're a bit all over the place. You're essentially doing random stuff. But the more trials you do, the closer and closer that proportion gets to the true value. Of course, these can change. For example, 0.33 we wanted. We haven't quite reached enough trials yet, but every time we do this, we get different ones. that graph jumped a bit. Why? Because at the start we weren't sampling any, so estimate was really low, and then we got up closer to 0.3. Whereas, say, same happened there, there, and there. But now the opposite's happening, where we start off with a really high estimate and then we're going down closer to 0.333. So I hope this demonstrates the law of large numbers. And of course we can use Excel to do much more complicated stuff. Rather than just sampling one roll of a dice, we could sample lots of rolls of a dice and look at the sum of them, or some function of them, and so on. And you don't need to know this, but just for background knowledge, when we do that, when we're sampling lots of things virtually, taking some function of them to try and estimate a probability of something, that is called Monte Carlo simulation. And that is way beyond this course, but that is one of the things I do in my research. I do Monte Carlo simulation for queuing systems.